Alibaba could open a door by saying, "Khul ja silsila." But that's an old story. Today, you don't need magic to do this for you. What you require is a knowledge of radiations and their properties. So how does chemistry help you open doors? Meet me in the studio to find out. Hello and welcome to another exciting episode of Chemistry. I am Deobrato Goswami and today we will throw some light on radiations and their nature. In today's episode, we will study about electromagnetic radiations and blackbody radiation. Then we will look at the Planck's quantum theory, which will be followed by photoelectric effect. And finally, we will move on to the most interesting exam decoded section. We know that light is a form of radiation and is a very common term that we use daily. But what is light and what are its characteristics? In earlier times, light was supposed to be made up of particles called corpusculates. But this was rejected when James Maxwell gave a comprehensive explanation about the interaction between charged bodies and the behavior of electric and magnetic fields on the macroscopic level. When an electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the form of waves. These waves are called electromagnetic waves or electromagnetic radiations. Let's study some of the properties of electromagnetic radiations. The first property is that oscillating electric and magnetic fields are produced by oscillating charged particles. These fields are perpendicular to each other and both are perpendicular to the direction of propagation of the wave. The second property of electromagnetic radiation is that they do not need a medium to travel. That means they can even travel in vacuum. There are many types of electromagnetic radiations. For example, visible light is an electromagnetic radiation. Now, the question arises, how do we characterize different types of electromagnetic radiations? Well, electromagnetic radiations are characterized in terms of wavelength, frequency, velocity, and wave number. Let us discuss each one of them. Wavelength may be defined as the distance between two neighboring crests or troughs of waves as shown. It is denoted by lambda. Next, we come to frequency, which may be defined as the number of waves which pass through a particular point in 1 second. It is denoted by the symbol nu. But what about the velocity? Velocity is denoted by v and is defined as the distance traveled by a wave in 1 second. In vacuum, all types of electromagnetic radiations travel with the same velocity. Its value is 3 into 10 to the power 8 meters per second. It is denoted by c. Can you tell me how are velocity, frequency and wavelength related? The relationship between velocity, wavelength and frequency is c is equal to nu multiplied by lambda. The next characteristic is wave number. It is defined as the number of wavelengths per unit length and is denoted by nu bar. Mathematically, it is defined as 1 by lambda. We have just studied the wave nature of electromagnetic radiation, but the wave nature of electromagnetic radiation could not explain some observations like blackbody radiation and photoelectric effect. Let us discuss each one by one. When solids are heated, they emit radiations over a wide range of wavelengths. So, let's take a common example of heating an iron rod and try to understand more about the phenomenon. When an iron rod is heated in a furnace, it turns dull red. As the temperature increases, it becomes more and more red. On further heating, the radiation becomes white and becomes blue at very high temperatures. The red color belongs to a lower frequency region and blue color belongs to a high frequency region of the electromagnetic spectrum. This means that as the temperature is increased, the radiation emitted goes from a lower frequency to a higher frequency or from longer wavelength to shorter wavelength. Well, an ideal body which emits and absorbs all frequencies is called a black body. The radiation emitted by such a body is called a black body radiation. The exact frequency distribution of the emitted radiation from a black body depends only on its temperature. At a particular temperature, intensity of radiation emitted increases with decrease in wavelength, reaches a maximum value, and then starts decreasing with further decrease in wavelength. Also, radiations of different wavelengths are emitted with different intensities. The most intense wavelength for a given black body depends on the absolute temperature of the black body. So, as you can see in the graph, the peak shifts from lambda 1 to lambda 2 with the increase in temperature, where lambda 2 is smaller than lambda 1. These observations could not be explained by the classical wave theory, according to which wavelength of emitted radiations should have remained same. However, intensity might have changed with rise in temperature, which is contradictory to the observation. For notes on electromagnetic and blackbody radiations, log on to www.topperlearning.com. It's time for a short break now, but I will leave you with something to think about. How are velocity, frequency, and wavelength related? I'll be back with the answer on the other side of the break. Till then, keep thinking. Welcome back. You are watching Chemistry 11 with me, Devabrata. Before the break, I asked you, how are velocity, frequency, and wavelength related? The answer is, the relationship between velocity, frequency, and wavelength is C is equal to nu multiplied by lambda. After understanding the relationship between velocity, wavelength, and frequency, let us now move on to our next topic for the day, that is Planck's quantum theory. The phenomenon of blackbody radiation could be successfully explained by Max Planck. He suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. I am sure there are a lot of questions in your mind, just like our young friend who has called in with a question.
Hello sir, I am Ritesh and I want to know what is a quantum.
That's an interesting question and an interesting concept. Planck gave the name quantum, meaning fixed amount, to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. He proposed that the energy E of a single quantum is proportional to its frequency. The equation is written as E is equal to h multiplied by nu. H is called Planck's constant and has a value of 6.626 times 10 raised to power minus 34 joules second. Energy is always emitted or absorbed as integral multiple of this quantum. This is also known as quantization of energy. In 1905, Planck's quantum theory was used by Albert Einstein to explain the photoelectric effect. And yes, that is our next topic of discussion. We define photoelectric effect as the phenomenon of ejection of electrons from the surface of metal when light of suitable frequency strikes it. The ejected electrons are called photoelectrons. The coming diagram will make its understanding easier. When light of a suitable frequency falls on the surface of the metal, electrons are ejected from its surface and move towards the positive electrode. These electrons constitute current. Let's see some results which were obtained from the experiment on photoelectric effect. As soon as the light strikes the metal surface, electrons are ejected immediately. That is, there is no time lag between striking of light beam and ejection of electrons from the surface. An important thing to remember here is that the number of electrons ejected is proportional to the intensity or brightness of light. Also, for each metal, there is a characteristic minimum frequency nu naught, below which photoelectric effect is not observed. If the frequency of light falling on the metal, that is nu, is greater than nu naught, then electrons are ejected from the metal surface, otherwise there is no ejection of electrons. Further, the ejected electrons will have some kinetic energy. For example, if we radiate a metal having low ionization enthalpy like potassium with red light, which has a frequency of about 4.3 to 4.6 times 10 to the power 14 Hz, for hours, there is no ejection of photoelectrons. If we replace red light with yellow light with frequency of about 5.1 to 5.2 times 10 to the power 14 Hz, the photoelectric effect is observed. This is because threshold frequency for potassium metal is 5.0 times 10 to the power 14 Hz. All these results could not be explained by the wave theory, according to which the energy of the light depends on the brightness of light, that is, its intensity. It was Einstein who was able to explain the photoelectric effect using Planck's quantum theory. To explain the photoelectric effect, Einstein assumed that the radiant energy striking the metal surface behaves not like a wave, but rather as if it were a stream of tiny energy packets. Each energy packet, called a photon, behaves like a tiny particle. When a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. The photon should have certain minimum frequency called threshold frequency nu naught. The minimum energy required to eject electrons is called photoelectric work function, denoted by W naught. Thus, the work function becomes W naught is equal to h into nu naught. If frequency of incident photon is less than threshold frequency, the energy of photon will be less than the minimum energy required to eject electrons, and hence no electrons are ejected, no matter if we increase intensity of light or increase the duration of incident radiation. On the other hand, if the incident photon has more energy than the energy required to remove the electron, then electrons are ejected from the metal surface. Pay attention because this is really important. Since the striking photon has energy h nu and minimum energy required for ejection of electrons is h nu naught, so h nu minus h nu naught energy is transferred to the ejected electron as kinetic energy. Since energy is conserved, the energy of ejected electron is given by equation 1, where me is the mass of electron, v is the velocity of ejected electron. This photoelectric effect has many applications in day-to-day life. Light of a suitable frequency is made to fall on a photocell. Electrons are ejected and hence a current is produced. When light reaching a photocell is interrupted by human beings or an object, there is a drop in photocurrent signals. The motor reverses and the door opens. In other words, magic. To know more, log on to www.topperlearning.com because studying smart is the way to crack your exams. Well, it's time for a short and quick break now. Don't go anywhere because our most challenging yet interesting segment, Exam Decoded, is waiting for you on the other side of the break. Welcome back. I am Devbroto and you are with me on Chemistry 11. Let's do a short revision of what we learned today. We studied that an ideal body which emits and absorbs all frequencies is called a black body. Radiation emitted by a black body is called a black body radiation. Planck gave the name quantum, meaning fixed amount, to the smallest quantity of energy that can be emitted or absorbed as electromagnetic radiation. The phenomenon of ejection of electrons from the surface of metal when light of suitable frequency strikes it is called photoelectric effect. Now it's time to test the knowledge. Yes, I'm talking about our most challenging segment, Exam Decoded. Welcome to Exam Decoded, and as usual, we will begin with the rapid fire round. Here are the rules. I will ask you 5 questions with multiple choices and you have to choose the correct option. You will get 5 seconds to answer each question, and for each correct answer, you can give yourself 1 mark. Here is the first question for you. Electromagnetic radiations do not need a medium to travel. True or false? This is true. Second question. Which of the following values of energy is not possible to be absorbed or emitted by a body? A. E is equal to h nu. B. E is equal to 14 h nu. C. E is equal to 2 h nu. D. E is equal to 1.5 h nu. The correct answer is option D, which is E is equal to 1.5 h nu. Here comes the next one. The minimum frequency required for ejection of electrons from a surface of a metal is called its A. Work function, B. Threshold energy, C. Threshold frequency, D. Quantum frequency. The answer is C. threshold frequency. Great going. Here comes the fourth question. According to Max Planck's quantum theory, energy is emitted or absorbed in small packets of energy called A. Quantum, B. Planck, C. Black body, D. Threshold. And the answer is A. Quantum. And finally, frequency is defined as the number of wavelengths per unit length. True or false? It's false. It's time to tally your scores now. If you got 5 on 5, you are a high flyer. You are all set to max scores in your exams. If you got between 3 or 4 on 5, then you are an achiever. And if you haven't scored above 3, then consider yourself still a learner. But don't worry, log on to our website www.topperlearning.com for tests and practice questions. The topic Planck's quantum theory belongs to the unit structure of atom, which carries a weightage of 6 marks. The questions asked from this topic can be very short answer type questions for 1 mark and short answer type questions for 2 or 3 marks. Since this chapter carries 6 marks, this chapter is critical from exam point of view. The questions covered from this topic usually test your knowledge and numerical ability. But knowledge is only part of the battle won. To be an out-and-out winner, you must also know how to present your answers. And here is an example. Calculate the minimum amount of energy that the photons must possess to eject electrons from cesium metal. Threshold frequency of cesium metal is 4.6 times 10 to the power 14 second inverse. The value of Planck's constant is given as 6.63 times 10 to the power minus 34 joules second. This question has a weightage of 2 marks. Threshold frequency is the minimum frequency that photons must possess to eject electrons from metals. The value of threshold frequency of cesium metal is given as 4.6 times 10 to the power 14 second inverse. Now, the minimum amount of energy required to eject electrons is work function. We know that the formula of work function W0 is equal to h nu naught. This will fetch you 1 mark. Substituting the values of h and nu naught in the formula and calculating gives the answer as 3.05 into 10 to the power minus 19 joules. This will fetch you 1 mark. I hope this cleared your concepts, but if you have any doubts, do drop us a line at www.topperlearning.com. Now it's time to say goodbye. But before leaving, let me ask you a simple question. Night vision devices help in viewing the objects at night. But how do they work? Well, night vision devices work by using photoelectric effect. This is Debabrato signing off for today. Wish you all the best for your studies. Goodbye.